Morning. Let's get started. Good. Yeah. Morning. For the folks who are on their phone, could they put away their phone, please? Thank you. Cool. Yeah. So today we'll just finish with. Last time we were doing interconnect networks, so we're going to finish that. And I don't think it will take me the whole time, so we can look a little bit at the third programming assignment after we finish. Yeah. So just to recap from last time, we were looking at this table, which is just a table of the bounds that we get from the different type of interconnects. And specifically, we're focusing on meshes and torus, and we were examining like 2D and 3D. We're examining 2D, and previously we had also looked at 3D and going up to arbitrary k dimensions, or d dimensions, where the number of processors is k raised to d. And we can see that the diameter, which we want to go down, is decreasing polynomially with the dimension, so that is good. It increases linearly here, but this is dropping faster than this increases. So it seems that we should try to increase the dimension as much as possible there. And we see a similar thing here, which is that the bisection width is getting closer to 1 with smaller d, or with larger d, because like 1 minus 1 over d gets closer to 1 as d goes to infinity. And the cost does increase, but the cost increases linearly with a number of dimensions. So it doesn't increase that much. These are polynomial increases, but this is only a linear increase. So looking at this, it seems like we should be increasing the dimension as much as possible. Yeah. Okay, so how would we maximize the mesh dimensionality? Well, we can take an example. Suppose we had 32 processors. How many dimensions can we make? Well, in 2D, 32 is not a power. 32 is not a perfect square, so we can put 8 and 4. And then in 3D, we can put 4, 4, and 2, and so on like that, up to 5D. And then we would put 2 in each dimension, because 32 is 2 to the 5. And we can't go any further, because it doesn't make any sense to put one processor in a single dimension, because that would just be pretty much the same as the previous dimension. So yeah, and at 2D, it doesn't make any sense to make a torus either, because there's only 2 neighbors in each dimension. So like it would just double the links between the 2 neighbors. So we would just focus on mesh in the maximum dimension. And so it seems like to maximize the dimensionality, of course, it depends on P, which is the number of processors. So that determines how many dimensions we can get. And for P, if P is a power of 2, 2 to the D, then it seems like we can choose log P as the number of dimensions, which would put 2 in each of the dimensions. And one cool thing about this is that this is like a hypercube. So a hypercube had, in some ways, you can view it as a mesh with log P dimensions. So if you think of it as dimension equals to log P, and number of processors is 2 to the D, the properties of the hypercube kind of fall out of the properties of the mesh that we were talking about. So diameter was this thing, which is just log P. And that makes sense because the diameter is the max path through the entire interconnect. And the maximum, if you view it as like a log P bit string, the maximum number of bits that need to flip between any 2 processors is log P. Because 2 processors in a hypercube can differ by only at most log P bits. And then a similar thing falls out of the bisection width, which is that P, this 1 minus 1 over D is the same as this, P 1 over P to the 1 over D, and that is P over 2, if D is log P. Yeah, if D is log P, or another way to say it, P is 2 to the D. So 2 to the D times 1 over D is 2. And yeah, so that is something interesting, because like so far we have been thinking of meshes and hypercubes as separate types of topologies, but actually in the limit, they are basically the same thing. And the kind of, maybe like a lot of the properties why hypercubes are nice sort of fall out of this connection. We have been talking about this the entire time, which is when we adjust the processors in the hypercube, we look at the bit string, and there's just 0 or 1 in each bit position, and that's log P bits. And now this is just a mesh with each of them is 1 dimension, each of the bits is 1 dimension, and the 2 processors are just 0 or 1 in each dimension. And if you want to find the neighbors, we have been doing this also, you have some bit string, you flip one of the bits, and that's your neighbor along that dimension. So this is just a concrete example. We have this bit string 100, 101 in the 6-dimensional hypercube. And to find the neighbor, you just flip the bit 0 or 1, and it's like a mesh. But each processor is a corner processor because there's just two. So that would be the end of the mesh. And again, there's no torus because that would just be the same, like 0, 1. Yeah. So this is pretty much what we have been doing so far, but just in the context of interconnect. Yeah. And again, the diameter is at most log p. Each node has log p neighbors. And the distance between two nodes is given by the bit positions. So the edit distance in terms of bits is the distance in terms of wires that any two processors would be. That make sense so far? Okay. So one way to view hypercubes is that we can construct them from hypercubes with lower dimension. So in 0 dimensions, we just have 1 point. And then in 1 dimension, we have a line 0 and 1. And basically, you can think of this as you have a hypercube of dimension d minus 1. And if you want to construct a hypercube of dimension d, then you prepend 1 bit in the front, half of them, and then that doubles your space. Half of them are 0 and half of them are 1, and the lower bits are all the same. So like this is 0 and 1, this is 0. You can think of like this is a line, and then we put 0 in the front of here and 1 in the front of here. And then you also have to connect those things that differ by 1 bit as well. And then same with 2D, like now you have a square and then you want to make a cube. So you stack 2 squares on top of each other and you put the lines like going down into the dimensions as well. And you see a similar construction like 0, 0, now this is 0, 0. But now 0, 0 spawns 2 things like 0, 0 and 1, 0, 0. So, and then so on as you go higher up into arbitrary dimensions. And this is kind of nice because it's not only is it a way to construct the hypercube, but it's also like suppose that you had this machine and it has this hypercube topology and it has a lot of processors in it, and you want to split up the processors among some users. Like you have 2 users and they want to run separate jobs. The hypercube is easily splittable, like because we constructed it from the lower dimensions, you can easily split it into 2 of lower dimension as well. So you could give one user like half the hypercube, and you could give one user the other half of the hypercube, and they would both be running independently with no contention, or yeah, with no conflicts as well, because if they just run in their own little world like here and here, then they just, they do their own thing, they run on the hypercube with whatever algorithms, and they don't need to handle each other at all. And this can be done recursively as well. So like here, if you split this into half, then you could also split this one into 2D and then give those off as well. So it has this nice recursive property. So hypercubes are good, and we've been doing them for a lot of the algorithms in this class. There's some difficulty in actually constructing true hypercubes in practice because, like I said kind of earlier last time, it is hard. Like we live in 3D space, so you have to embed the actual thing that you're trying to build into 3D space. And ideally, when you build them, you want to minimize the number of wire crossings as much as possible. So ideally, it would be able to be laid into something like 2D space. Yeah, and also another difficulty is like we want to grow the maximum number of ports you need grows with p. Like the maximum number of ports is log p because the neighbors is log p. However, like when you build a machine, it has a fixed number of ports, so you cannot just arbitrarily grow the ports. So in practice, you just have to fix a maximum dimension, and that's limited by the number of ports we have. So that would be log p. And also, arbitrary dimensional hypercubes cannot be embedded into physical 3D space well without crossing links. So that's another challenge when we build these physical things. One thing we'll talk about immediately is the solution is that basically it's kind of like the tree thing that we were doing before, which is that you spread the thing over multiple stages. And the reasoning for that is because it addresses these challenges. One is crossing links, and another is some of the cables don't have uniform length, which is another problem when you build these things. Yeah, so these days nobody really builds true hypercubes, but they do build things based on hypercubes. So the most easiest way to flatten the hypercube is in something called a butterfly network. And in a butterfly network, so if you remember, like in a hypercube, there are p processors. P is 2 to the d for some dimension d. And in a butterfly network, it's basically like the hypercube algorithms, but in rounds. Like usually these algorithms with p processors, and they happen in log p rounds, where in each round you connect one bit flips, and it's a different bit in each round. So like the first bit would flip, and that would be your neighbor in the first round, and the second bit would flip, and that would be your neighbor in the second round, and so on like that. So now there are log p stages, and so the number of processors becomes p log p. And there are p in each stage. So you can think of the columns as the actual hypercube processors, and the stages are kind of like the stages for the algorithm horizontally. So the x dimension is like time, the y dimension is the actual processors, but this is a physical thing, so you actually do build p log p processors. And in practice, we can use p log p processors. We just can't use like polynomial in p. Yeah, and the horizontal links are just connecting like the same processor across time, and the crossing ones are the links between neighbors in the hypercube. And this is also good because it has a fixed number of links per node, like the number of neighbors at each round is 2. So you just need 2 ports. It doesn't grow with p anymore.
Are they actually p-log-p processors, or are they p processors which you assume to be in log?
I see. No, there are actually p log p processors. Yeah, but these are thought to be like, you can imagine like an algorithm running this way, over this way, and then at the end, like these are all kind of representing the same processor in some sense, but the final result would be like here, or here if you're going this way. Yes, yeah, exactly. Exactly, yeah. But it's kind of following like a lot of the algorithms that we did before, they follow this pattern, like you fix one bit and then you just move the bit that changes along. So that's kind of the inspiration for this design.
For example, this is one typical communication of broadcast.
Yeah.
But let's say we want to do that in place all the other, but when we have to do it, we have to do some modifications.
Oh, yes, because you can't use a full hypercube here. Yes. Yeah, this only lets you do like one stage of one stage of the hypercube. I guess you could run it over multiple stages in parallel to implement the in place altogether, for example. Like the first step would be like here, and then you could also run like here and here simultaneously. Good question. That is butterflies. And butterflies are basically just flattening of hypercubes. Oh, yes. Oh, because to reduce the number of neighbors per node. Or one of the main reasons is that if you want to build a true hypercube, the number of neighbors per node grows with p, which is hard to build in an actual machine. So ideally, we would like to fix the neighbors per node to be something small. And also another reason is that building a true hypercube is hard to do in 3D space because like the links become, like even if you look at this, like these links are different length than these links when you do the connections. Different length. Yeah. They're, oh, like in terms of physical length, like when you actually build a physical wire. Yeah, like logically they're one apart, but there's not really a way to arrange such that all of these like all of these curved things would be the same length as all of these like horizontal or vertical lines. And it's even hard to arrange all of these curved things to be the same length as each other. So in 3D space. So that's the difficulty, and that's why we wanted to flatten it. Thank you. Yep. Cool. Yeah. So far we have been talking only about static networks. And if you remember last time, I said there's two kinds of networks. There's static and dynamic. And the difference is that static, you just have point-to-point links. And in dynamic, you can connect to switching elements as well, which perform routing between the different processors. And the basic switching element is a 2x2 crossbar. So you can think of it as this box, and there's two input wires. And either the input wires can just pass through to the two outputs, like top and bottom, or they can swap, top goes to bottom and bottom goes to top. And yeah, you can connect any two inputs to any two outputs. And so we're going to use this switching element to build a type of network. And first, we're going to define this perfect shuffle, which is the type of network that we want to build. And in this perfect shuffle, the high-level goal is that we want to route arbitrary hypercubic permutations, because that will enable us to implement a lot of algorithms. So the way we're going to do it is kind of like, you can think of it as like if you have a deck of cards, and you do a perfect shuffle, which is like you put one from left side and one from right side, and then one from left side and one from right side, and so on like that. So that is what this is. So if this is your deck of cards, numbered 0 through 8, then one from the left side is 0, one from the right side is 4, one from the left side is 2, one from the right side is 5, and then same for 2, 6, 3, 7. So this is like the first stage. We started, this is the left and this is the right. And then we went to the next stage, which is now, this is the left and this is the right. And then we do it again. And so now this is the left, this is the right, and we take, again, like one from the left, which is 0, one from the right, which is 2, one from the left, which is 4, one from the right, which is 6, and so on like that. So that builds us this first left thing. And then we build the right one in the same way, which is one from the left, one from the right, one from the left, one from the right. So that's 1, 3, 5, 7. And if you do that again, so that is this. So this is the first stage, which we have built. This one. And then the second stage is that one. And then finally, if you do it again, you can notice that this is what we started with. Good question. So the first line is processors. When you actually build it, the first column is processors, and these are switching elements in the remaining stages. And the goal, if you remember, like we're trying to route hypercubic permutations. So like then at the end, it would just wrap around the switching element. So like these are all switching elements, and you want to route stuff from these processors back around into arbitrary permutations into these processors again. Good point. So this would be P processors and P log P switching elements. P minus 1 log P, I guess. And one really cool thing about this is that the communication, so these are the connections between the switching elements. And one nice thing is that the communication pattern is the same across the stages, because you always do this perfect shuffle, and the wires tell you the direction of the perfect shuffle. So this was like the first one from the left, then the first one from the right, then the first one from the left, or second one from the left, and the second one from the right, and so on like that. Third one from the left, third one from the right, fourth one from the left, fourth one from the right. And you just copy it repeatedly. And that forms the basis for something called omega network. And in omega network, you have P over 2 log P switching nodes. So these are the processors on the very left side. You put the switching nodes in the middle, and then there's P over 2 of them because each one of them has 2 inputs. And then there's log P stages. So that's where we got. It's order P log P. And yeah, and then so the goal is that, and you can think of these outer links, they're just wrapping around to the initial ones. And I'm going to show that you can route hypercubes through this. Yes. Yes. We can route arbitrary hypercubic permutations through this. Where hypercubic permutations are you flip one bit. Like everybody has, you have to fix the bit that flips. So for example, let's say we pick the most significant one. Everybody would flip their first one, for example, and then this would route to 0, 1, 1. This would route to 0, 0, 0. This would route to 1, 1, 1, so on like that. Did I answer your question? Yeah. So yeah, if you remember, the goal is that we want to route strict hypercubic permutations, which is that everybody has to. We fix one bit, and everybody has to flip that bit. And if we run it again, we could flip a different bit. But like, yes. Yes, we will do that in one moment. Yes, yeah, thank you. Okay, so yeah, so this is maybe what you're talking about. You can tell me at the end if I didn't answer your question. So the way that you route things through this is through what is called destination tag algorithm, or DTA. And the way it works is kind of cool, is that you only need to consider the bits of the destination processor. And the algorithm is very simple. It's so every switching network has a top and a bottom part. If the bit at the current stage is 0, then you route to the upper output. If the bit from the current stage is 1, then you route through the lower output. And one cool thing is that you can see that it doesn't depend. The actual routing does not depend on the source processor. Of course, you need a source processor, but that's already kind of like given up front. And the source processor, each one has only one output. So you don't need to think too hard about where it's going to go from there. So that's why we start taking the bits from most significant to least significant, starting at the initial switching element. So here, for example, let's say we're trying to route 0, 1, 0 to 1, 0, 1. So 0, 1, 0, and then this just has one output wire to some switching element, so we don't have to, that doesn't depend on any bits. And then, so the first most significant bit of the destination is 1. So we say, okay, it's 1, we're going to route it out of the bottom part. So that brings us to the switching element. And now this switching element, we're taking the bits from most to least, so that's 0. So according to this algorithm, we route it out the top part. And then here we see 1, so we route it out the bottom part. And you can see that this is indeed 1, 0, 1. Does that answer your question? Mm-hmm. Yeah. So that's cool because it is only dependent on the destination bit string, and it doesn't have any it doesn't have any conflict with, then, like, it doesn't depend on the initial one, except for the fact that it needed to come out of the initial wire, and we know where that was. Mm-hmm. Uh-huh. Yeah, so let's take another example. So for example, let's just say, I don't know, 0, 0, 0, 0. So 1. So it has to come out here, 1. And then according to 1, it will go out the bottom. So here, 0, here, 1. Yeah, it's weird in that it doesn't depend on it just has to go out the input wire, like the initial wire, but after that, its path through the switching element is determined by only the destination. In a moment, I'll tell you why it's working, because it's nice, like it's very simple. Okay, and why does it work? Well, it's based on the perfect shuffle. And you can think of the perfect shuffle as bringing together the pairs with the most significant bit. So, like in the first round, you can think of it as you flipped the first most significant bit. Like 0 is 0, 0, 0, 4 is 1, 0, 0. And then 1 is 0, 0, 1, 5 is 1, 0, 1, and so on like that. And then in the second round, you flip like the second bit. So this is like 0, 1, 0. Sorry, this is 0, 0, 0. This is 0, 1, 0. This is 1, 0, 0. This is 1, 1, 0. And then like that, and so on. And then this one is, you come back around, and that's just, you flip the least significant bit, because we just have 3 bits. So that's, like I promised, you come back to the original ordering. And the way that this is working is that the bottom output, flips the bit at that level. And the top part just keeps that bit the same. So like, let's just look at this example, 2. Just goes to 2 here. The top wire for 2 is just the same 0, 1, 0. The bottom wire is 110, so you flip the top bit. And then same here, like this is the box. The top one is you flip the middle bit. This would be 110, and this is 100, this is 110, and then so on like this, the same. Does that make sense? Yeah, and so that's why that works, is because it's based on this perfect shuffle, which it's just flipping the bits from left to right in each stage. Okay. So we want to write hypercubic permutations, and just for completeness, this cannot route, it can route arbitrary permutations, but maybe not very efficiently. So we can just look at one example, which is suppose that we had 100, 010 going to 111, and then 110 going to 100. So this is changing in 2 bits. Like these were 2 zeros, and then this changes in 2 places. And this is only changing in 1 bit. The middle bit flipped from 1 to 0. And you can see that these are the 2 paths going through the connection network. And we get some, so dotted line, 2 dotted lines. And you can see we are getting some congestion out on this wire. Both of them want to route to this one. But however, like an omega network can route arbitrary hypercubic permutations with no congestion, because in sometimes each switching element is flipping 1 bit, and in hypercubic permutations you fix the bit that is going to be flipped, and then so both of them would route out different ways. This is just one example of how you route one hypercubic permutation through the omega network. So here, like this is an example, 000 is going to 100. So the first bit is getting flipped. And then same here, like we expect 011, and indeed it is 011.
Multiple, all of these inputs flip either MSB, LSB, any bit, then all of the communication can go through without congestion.
Yes, if all of the inputs choose the same bit to flip, then they can route through with no congestion. And the reason, you can kind of see it in this picture, which is that at one stage we will do cross, and then at the other stages we all do pass through. The congestion comes from like if both of them want to come out the same wire. But because the way we set up the permutation, it wouldn't happen in this case. All good? Any questions? Okay. I think that is the end of interconnects. Oops. So everyone can see this? Yeah. So we'll just do a quick, well, it doesn't need to be that fast, it's 8:30. We'll just do a regular pass through programming assignment 3. So maybe like, has anybody looked at this? You can tell me. Yeah, okay, yeah. I just wanted to make sure that I wasn't like wasting anyone's time by doing this. So yeah. Like I promised a while ago, the high level assignment is doing sparse matrix multiplication. And so we can read this in this assignment. You will first, this is a theoretical thing, you show that triangle counting and breadth first search can be performed using matrix multiply, which is just C equals A times B for some A and some B. That's theoretical, the first part. And then the second part is to implement a basic sparse matrix multiplication to perform sparse matrix multiply. And then the third one is to perform breadth first search using this. So once you implement this, you should use the sparse matrix that has been implemented to subroutines in breadth first search and triangle counting. And I claim that outside of this is the hard part, and these are just kind of like wrappers over the function, and maybe there's a little bit of thinking that needs to go into what exactly are A and B that need to go in here. But once you set up A and B right, then it should be, the actual computation part is just mostly in the SPGEM. So the first step is in the report to explain or prove how matrix multiplication can be used to do triangle counting and breadth first search. So yeah, so the high level point of this homework is that there is this connection between graphs and matrices. So SPGEM is clearly a matrix algorithm, sparse matrix, multiply, but clearly triangle counting and breadth first search are graph algorithms. And there's this connection computationally and also algorithmically between these two things. Like we talked about earlier, adjacency matrix is used for both graph and matrices. And these formats like COO that we did, which is just like pairs of tuples, and CSR, which is like the array-based thing that we were talking earlier, both are used heavily for both sparse graph and sparse matrices. So this is just explaining what is triangle counting. Triangle counting is you have a graph, and here we're going to do directed graphs, and you want to count like you have three vertices A, B, C. If there's edge like AB, BC, CA, that's one triangle. And that is just like a popular graph algorithm. And if you think about how to implement it in a graph way, one of the straightforward ways to do it is that you go through the edges that you have, like suppose vertices, you go through the edges that you have, and each edge has two endpoints, A and B, and you know that there's an edge from A to B because you just looked at that edge. So you just look through both of their neighbor lists. Like you have some representation that allows you access to see all of A's outgoing edges and all of, well, you kind of need the incoming edges, but anyway, you need some representation that gives you all of B's outgoing edges and all of A's ingoing edges. And then, because you want to see if there's some separate vertex B that gets you B to C and then C to A. Make sense? So you can imagine implementing it directly, iteratively on top of the graph representation. But here, in this case, we're going to show that you can also do it through matrix multiply. And the high level intuition is that with some matrix multiply, or yeah, let's talk about undirected graphs for a second. Matrix multiply gives you the two hop neighbors. So that is one key step that we need to, way to think of triangle counting is to get the wedges and then to figure out where the wedges close. Does that make sense? And the core part of this implementation is to do sparse matrix multiply, which is just the same matrix multiply that we have been doing, but it looks very different in the sparse case because almost all of the elements are 0. So talk a little bit, I think next time we'll do sparse matrix vector, but you don't need sparse matrix vector really to do this. We have already covered everything that you need for this mostly, which is sparse matrix representations. So like if you remember COO format, which is a list of tuples, that is the core of this algorithm. So thinking about how to run most of the iterations that you have to do are through the rows. So thinking about how to do the iteration effectively through the rows, or maybe it may even help to convert it into a different format, like for example, compressed sparse rows. So it would be, the input would be given in COO in tuple form, and you can think about how to convert that into CSR, which is in arrays. It's not too hard. You have a list of tuples, and it's sorted. So you, in CSR, like you have two arrays. You have one which is the edges in sorted order by source, and then you have the offsets. So the edges are already given. Those are just the second element in the tuple. And you just need to figure out how to build the offsets from that. And that is just, you know how many the offsets in some sense is like the count of how many edges come from the same source. Another thing, you may see it in the handout, don't remember, is that sometimes in this assignment it may help you to take matrix transpose. So because the graphs are directed, uh, the initial graph is given as like all the outgoing edges, u to v. But if you do the matrix transpose, it gives you the incoming edges, v to u. So sometimes, like depending on the algorithm, you may want the incoming edges. Sometimes you may want the outgoing edges. Okay. And I suggest here to implement Gustafson's algorithm for sparse matrix, sparse matrix. So like the easiest way to do or the most straightforward thinking way to do matrix matrix is like, you know, you have a row, you have a column, and you just go row, column, like that. However, the problem with that is that the second representation needs to be in column format, or like ideally it needs to be in column major order because you want fast iteration through the columns, which is fine. That is definitely possible to do. But if you keep, there's one way to do it, or there is a way to do it. There's probably more than one way. If you keep both A and B in row major format. And that way is called Gustafson's algorithm, which is this old algorithm for doing SPGEM. And nice. So you have initial matrix C. Oh yeah, another challenge here is when we did dense matrix multiplication, you know the size of the output. Like C is equal to, like if it's MKN, you know C is MN. Here, the maximum dimensions for C are also MN, but you will not have nearly MN non-zeros. So the output sparsity also depends on the inputs. So you just gotta be careful about it. It's not like there are clearly many ways to deal with this, and any way is probably fine. But you just it will not work to realize the entire dense matrix C because the reason for sparse representations is that often the dimensions are too big to realize the dense format. Okay. So this is the way this works. You take your matrix A and you loop over the rows. So you fix the row I and you just look at all the columns. So you have AI star, where this is just some non-zero in A. And then for every AIK in that row, so K is the inner dimension, you do for all the BKJ in B sub K. So normally when you do row column, you can think of it as C is stationary, where C is like the matrix element that you're outputting, because once you finish one row and one full column, you have finished all of Cij. Here, you have not finished all of Cij, but by the end of the algorithm you will have, but like after a single row, you will not have finished all of Cij. But you will have but some partial sums into Cij. And yeah, so you look at all the non-zeros in row A, you look at all the non-zeros in row, you match the inner dimension. So this is row K of B, and J varies. So the actual element of C that you're updating is Cij. But like if you go to, for example, BK plus 1, there may be another like BK plus 1J. And then there you would have to update Cij as well. So that's what I'm saying. Like in every row, like we're not finishing the entire output element, but after all the rows, you finish it. And then you get this value, which is just the thing that we're accumulating into C, which is, again, the multiplication, AIK times BKJ is just the same as always. And here, if this is just saying if we have already accumulated something into the Cij, then we update it. Otherwise, we just set it to the value. Yes.
The first few lines, until line 5 and all, we're just doing an element wise. Until line 5, we're just doing element wise multiplication of A and B. And then we are checking if the intermediate product which we got currently will be directly contributing to C in the current processor, or will it needs to be communicated to another row of the
It depends on what. It's a good question. It depends on what rows and columns of C. It depends on what distribution of A, B, and C are there. There is. So, for example, we'll talk about it later. Like, suppose the most natural thing we block distribute A, B, and C. Like we cut we just cut the rows evenly and we ship them off to the different processors. And ideally, processor 0 would be responsible, or any processor is just responsible for computing its own submatrix of C. And so then we need to think about what parts of A, B, and C do we need for that. The most easiest way, so like, is it clear that, I need a pen, give me a second. Okay, so let's just say we have 3 processors. We have, and this is how we're going to cut A, B, and C. I don't know, it's just a picture. Like that. And so suppose, so this is like M by K, this is K by N, this is M by N. And then we need to compute, this is an M over P times N submatrix of C. And what are the elements that we need to compute that? Well, this is sufficient. This is M over P times K submatrix of A. This is fine, but you need all of B. You can probably, as a start, you can just replicate B. Like, it will be initially given block distributed, but you can do an all gather, and you would get all of B. And then clearly, like, this and this is sufficient to make that. To reduce, so that is minimal in communication, because like you just do initial all gather, and then everybody has B, and everybody has all they need, and there's no subsequent rounds of communication. Another thing that you could do is, in this block distributed part, you could rotate B. Like you put columns 1 through P, and you can rotate B. Probably initial good implementation, like the initial easiest implementation that is still fine, is you just all gather B. Because everybody starts out with the A and the C that they need, but they don't yet start out with all the B that they need, because you need to go through all the rows. So you can think of each processor, you're doing, the inner loop is the same, but this just is not through row, it's not through all of AI. It's not through all of AI. It's through like a chunk, it's like through a chunk of AI in parallel, where each processor is like the in parallel part. Does that make sense? Yeah. So the actual iteration is the easy part, and actually this all gather is also quite easy. The hard part, it's not even that hard, but the challenging part is you got to think about what representation you use for C, because C is initially empty. And it could also start simple, like it could be anything, like a vector of vectors, or like a vector of hash maps, because you need to efficiently support this insert and check. So often in many cases, a vector is totally fine, even though, like, of course, you need to iterate through the vector to check if something is already there. One way to save it is like you could keep it sorted, and then that might short circuit your search. Another way is, usually these are the length of C, or the length of any row is actually quite small. Like the average degree is usually less than 100. So, I mean, some would be, in some graphs, like some rows would be long, but almost all of them are short. So it's a representation question. A vector is probably a good way to start. Yeah, so this is just some implementation detail. It's just, you have a pair, which is a row and column tuple, and then that's given in a pair as well with the corresponding value, which is like the weight. Pretty natural. And that is COL. And then to test the actual SPGEM implementation, like the actual just SPGEM function, we'll just do A times AT, where A is a square. Just to run it. Mm-hmm. What order is this? What do you mean? Oh, it will be sorted by row and then column. Yeah. Actually, if you look at the, if you have time, probably with them. And then I can show you like a little bit of the testing harness. And we already do the block distribution for you. You don't have to think about, yeah, but the subparts will be sorted already. The input will be sorted. The output should ideally be sorted, but actually I think we post-sort it as well. So maybe you don't even have to do that if it's easier. I can check exactly in the test harness, but I think it's post-sorted, which is not counted in the time. Just to do like, in the end, we have to do the validation. And so like to do the validation, the C tuples need to line up with the expected C tuples. And the easiest way to check that is by sorting the output, the experimental output, and then comparing it. Yeah, it's given in sorted by row and then sorted by column within the rows. So maybe one suggestion that I have is to convert this into CSR first, because it will make your iteration easier. Because you want to, like this loop, you can think of it on the processor as breaking this down into two. The outer one is parallel and the inner one is over the block. And then, so the inner one still needs to iterate over the rows individually. Okay. So yeah, so the initial, just to test the actual SPGEM, is just on A times AT. But the SPGEM should work on arbitrary dimensions, MKN, because later when you use it for BFS, for example, the things are not square, or one of the things is not square. Yeah. So this, maybe I should not tell you how to do it fully because this is part of the assignment, but the goal is to use the previously implemented SPGEM to form the BFS, and the input is an adjacency matrix in COO form and a source matrix, or a source vector, or, no, a source vertex, because you need to do BFS from a source. And the output, please lower down, the output is a vector of depths, where depths is the distance from the source. Yeah, and then like I said, next you use SPGEM to do triangle counting. And then the input graph is given in COO format of the adjacency matrix. The triangle counts takes the number of nodes. Da, da, da. This is what I said in the beginning. It's directed. So if and the only difference in the directed case is that if you have something like, for example, A, B, C, A, like A to B, B to C, C to A, that's one triangle. And then if you have the reverse, like A to C, C to B, B to A, that's another triangle. Yeah. Any questions so far? Mm-hmm. No, that's already done. Yeah. Like the block distribution is just done in the simplest way, which is like M over P rounded to the nearest thing times N, like this block distribution. Yes, they'll already be given in this form. Mm-hmm. Yeah. No, you keep a visited. You keep the visited array. You need to mark somehow what has been seen already. Uh-huh. Mm-hmm. The output is the depths, but you can make an additional vector. Yeah, you don't have to. Yeah, you can use whatever additional space you need. Like you can keep visited, for example, or you can dual keep visited as depth as well. Mm-hmm. Yeah. So the question was in BFS. Like I said, in triangle counting, one matrix multiplication gets you all the two hop neighbors. In BFS, you're basically counting the distance from every vertex, the minimum distance from every vertex, and somehow you need to keep track of the high level way this works is that you start with the source vertex. Like, okay, so think about how you normally implement BFS. Like you have a queue, and you put the source in the queue, and you just look at the head, and you iterate through all the neighbors of whatever was in the head, and you look at some visited array, and you check, have I already been visited? If yes, then do nothing. If no, then put me on the queue. And then you go around in the next round. That's how you would directly implement graph algorithms. To do it in matrix multiplication form, you kind of like, it's not really through this queue anymore. You keep a set of active vertices, which is the set of vertices that are distance k from you, where k is bad, I already used k. Distance d from you, where d is the number of rounds of SPGEM you've already done. And then somehow you need to keep track of which ones you have seen already. You could keep that, you could use the distances, the output is a distances vector. You can use -1 to say that it has not been visited. And indeed, like if there's more than one connected component, you may not visit everything, depending on where the source is. So stuff can be -1 in the output, but -1 just means I have not been touched. All good? Yeah, so this is just the same as in all the assignments. You pull it from Git. These are the codes. You have to fill in these SPGEM, BFS, triangle counts. And then the test driver, you can change it if you like if you want to print something or you want to write your own validation. But in the actual testing, we just will keep the initial main file. And like this is the same in all the other homeworks. We keep the same test driver and we run it. You can change it however you like, but you should make sure that it runs with the initial one. Yeah, another thing to notice is the input files are given on Canvas. So it's like a text, the zip file on Canvas. And it's just in the, if you go to like program assignment 3, there's two things. There's this handout, and then there's a zip file. And the zip file has 3 text files, which are just these inputs. Yeah, and the inputs look like this. They're given in this format. The number of nodes. Yes. Oh, I have to turn it on maybe. The number of nodes in the file. The number of, this is the source node that we're going to run the BFS, number of edges, and then the way the file IO is already done. You don't have to do any file IO, but just to understand what's going on, this is the number of edges, and we're just going to read 48 lines after this to get the edge tuples. And then there's some other stuff written in this file, like the output, the correct output, because we read the correct output for validation, which is for SPGEM, it's just the A times A transpose concatenated in the same format. And then the BFS vector, which is this distance from the source node. And then finally is the triangle count. Triangle count is just one number. Okay. Yeah, this is just the same. You can look through the files. The actual files that implement this stuff is SPGEM, BFS, and triangle counts. The make file is already there. This is the same as always on pace, and this is how to run it. These are the function. Oh yeah, to run it, you can run this binary PA3 and then the flag, which are, these are the flag options, SPGEM, BFS, or TC to run SPGEM, BFS, or TC, and the input file. So the inputs are like, like input 1, input 2, input 3, going up in size. So input 1 is mostly just to do, it's just to run very fast to do an initial testing for correctness. And then once you are working on input 1, then you can move on to the larger ones. Input 1, I think, is just less than 100 edges. It's very small, but just to do testing. And the function header, I guess here is MHN, but it's HSK, it's the inner dimension. And then these are A, B, and C in block distributed form in the tuples I promised. This is the row column, this is the value, and you have to fill this out, which is C. Da-da-da. Same as always. Yeah, so like I said, this will be in row wise 1D, which is just this picture over there. And if the rows are not evenly divided by the number of processors, then some processors will just get extra. So this example, like suppose you have 17 rows and 5 processors, these two would get extra. This is already done, like you don't have to do any block distribution, just to understand what's happening. BFS, it has this file heading, function heading, takes in the number of nodes, the source vertex, the graph in CO form, and the output vector. And then the graph is also block distributed. Triangle counts. Triangle counts is somewhat easier. It's just the number of nodes in the graph. And that is, oh yeah, okay, so these are the 3 functions, spgem, BFS, and triangle counting. And you can just see these numbers. These are based on the TA implementation. So that's where we got these baselines. They're not just made up at the TAs to run it. Yeah, on input 2, which is the biggest input. And yeah, so there's this, which is full marks, and then this, which is partial credit. Yeah, I don't know, correctness, runtime. And then the report, which is to explain your implementation, show that you can do BFS and triangle counting with spgem, and then report the performance and scaling on 1 in 16 for all these 3 functions on input2.txt. That's pretty much like the previous ones. Okay. Yeah, and this is just citations and how to use a makefile. You don't really have to think about the makefile, it's already there. But questions so far? Okay. We have a little bit of time. I can show you the code. Oh, no, I want to make this bigger. Okay. Is this size okay? Okay. So this is the repo, PA3. We had to make a small fix, so if you have already pulled it, please update it. It wasn't in any of the actual, like the structure is exactly the same. There's just a tiny issue in the test driver. So that has been fixed in like the block distribution part. But that does not change at all like the algorithm part. It only changed what you got as the input into the algorithm part, but it has been fixed. So all good. Almost all of them are, so like we can look at this, but this is just empty. This is the part you have to fill out, like spgem. But however, the most interesting part, because everything else is pretty much empty, is main. So, oops, okay. So this is just, let me make it a little bigger. Okay, so this is the test driver. And this is like this regular MPI, like initialization, you get the rank, you get your rank, you get the size. And this is just file parsing. So it has all already been done. You don't need to deal with this. And this takes in the flag, which is like BFS or spgem or TC, and then it takes in the file name. And then this is it takes in the edge list, or it fills it in. This is file AO. So it fills in edge list, fills in matrix A, it fills in A transpose, and some other stuff like what is the output of the spgem. This is all just, I don't know, file parsing. Okay, so everybody can get the number of edges, the BFS source, and number of nodes. Easy. And then this is just the part that does the block distributing. So this is saying you have your matrix A in COO, and we need to share it like in that form. So the way to do that is size is the number of ranks, and this is the number of um, rows that everybody will get, which is just nodes, which is equal to the number of rows, divided by size, which is equal to p. So everybody gets nodes over p rows, and then if it doesn't perfectly divide, you get a little extra. Yeah, this is not super interesting. This is just how you find the indices of the CO items that you need to send. But it is already done. So other stuff. This is not in the time, so doesn't really matter. Okay, so this is the part that actually sends the data, which is in scatter. So first, it sends how many everybody's going to get. So it sends A send count, B send count, C send counts, which is the number of non-zeros that everybody's going to get. And then we use that to make the vectors. And then from there, then we just get the data into the vector. Okay, so this is the actual part. Once we have received this, C should be empty. Yeah, so this is just, so we get the actual C, but obviously the function, this is just for validation, so everybody can do local validation. So we also scatter out the correct result, and later we'll check that, but the thing that actually gets filled in the function, this is blank, called C computed, and then C computed is passed into SPGEM. So this needs to get filled out, and in the end, we're going to validate this compared to this, and they got to be the same. And then the time is there. Yeah, so here we sort the output for C computed. It should be a list of tuples, and then just check if they're equal. And if they are equal, then flag is 1, and then there's reduction on the flag here. And in the end, total flag, which is a reduction on everybody's local flag, which is the local validation, should equal the size of the world. Yeah. And it's checked if total flag is equal to the size of the world, then the result is correct. And then the time is the max over the processors. And then otherwise it's wrong, and the time is still printed, but it needs to be correct. Like the time doesn't mean anything if it's wrong. And then it's it for SPGEM. Does that make sense? Any questions? So yeah, the most important thing about this is that you don't have to deal with any file I/O, and you don't have to deal with the block distributing part. That is already finished. So the only part that needs to be done is the actual matrix multiply. Because I asked the TAs to do it because I think last year, like when I was looking at the previous iterations, it was good in the sense that like it makes everybody learn how to write these test drivers, and like it was from scratch, like you had to write the make file also. But this is nice for some uniformity because then we can all just run everybody in the same test harness. So every approach has pros and cons, but this is what I'm trying out. Okay, so yeah, and then there's a similar test driver for everything else, like BFS. BFS is easy because there's no like A, B, and C to distribute. There's only A. Yeah, so this is just the same exactly as before, nodes over size, and then if there's extra, then you add 1. So this is the actual BFS part. Bigger. Yeah. So takes in the number of nodes, the source vertex, the data in COO, and a vector of node depth. And node depth is somewhere up there. Yeah, just there. Equal to n rows. And n rows is the number of rows divided by, it's like number of rows divided by p. So this is everybody's local depth vector. And in the end, everybody computed their local depth vector, and we gathered them all into one big depth vector, and then that's how the validation works. Yeah, rank 0, that's the validation. I guess it could also be local, but the rank vector is so small that, or sorry, the depth vector is small, so it doesn't really matter. Okay, and then triangle counting is the same, similar as before. You also only need to send A, which is the graph, equal to nodes over size, which is P. This stuff is extra. You just need to send it. Yeah. So the interesting part, you get nodes and you get CO, and you just have to output one int, which is a triangle count. Yeah, and that is, yeah, that's it. Questions? Concerns? So yeah, that's it. So thank you.